Hey, welcome back. Let's continue with the reaction of alkenes. This is the part 2. The biggest difference between alkenes and alkynes is that terminal alkynes are relatively acidic. When a terminal alkyne is treated with a strong base such as sodium amide, the terminal hydrogen is removed and acetylide anion is formed. But why are terminal alkynes more acidic than alkenes or alkynes? In other words, why acetylide anions are more stable than vinylic or alkyl anions? The simplest explanation involves the hybridization of the negatively charged carbon atom. An acetylide has an sp hybridization, which means that has 50% character S and 50% character P, which means that it is closer to the nucleus, more stable due to the negative charge. The negative charge and unshared electron pair on carbon make an acetylide anion strongly nucleophilic. As a result, an acetylide anion can react with an electrophile such as alkyl halides in a process that replaces the halide and yields a new alkyne product. We call such a reaction an alkylation because a new alkyl group has become attached to the starting alkyne. Alkyne alkylation is not limited to acetylene itself. Any terminal alkynes can be converted to its corresponding anion and then alkylated by treating with an alkyl halide, yielding an internal alkyne. The only drawback that has the alkylation process is that it can be used only with primary halides. With secondary and tertiary halides, it does not work. Okay, let's demonstrate this with some examples. This is a general form, like the terminal alkyne. This hydrogen here is acidic and can react with a strong base such as sodium amide and to give the acetylide anion that is on our interest. This hydrogen here has a pKa 25 compared to 35 of the sodium amide, which means that it is way more acidic than this base. This can also be explained with Bronsted and Lowry definition. I will link one of my videos in this video description to see them, what this definition means. In terms of why they are more acidic than the alkane and alkynes, is that, as I explained above, sp hybridization, 50 to 50. sp2, that are the double bonds, has 33 to 66, and single bond is 25 to 75. And if we draw the shells, you see that the s orbital is closer to the nucleus compared to p, which means that it's 50% here, which means that the negative charge and the lone pair on the acetylide anion, these ones here, gives them more stability. Let's move to the first example. You have the acetylide ion here, and it's going to react with a primary halide. It's going to happen the alkylation, and the final product is okay. So we have addition of one methyl group here. Let's move to point B. The first step is because here we have directly the alkyne, so it's going to react first step to form the acetylide anion, and after that it's going to do the alkylation from the alkyl halides. So the product is going to be the addition of 1, 2, 3 carbons. 1, 2, 3 carbons. Let's fill with hydrogens. Okay, this is the final product. From acetylene, we can form the terminal alkynes. So from this one, we can form this alkyne. That is a terminal alkyne. Okay? Doesn't matter how many carbons you have here. And we can continue adding this product here and adding more carbons. Okay, we add these 2 carbons here. As I mentioned previously, the main drawback that this method has, it works only with primary halides. If it's secondary, it's not going to give the desired product that we want here, but it's going to happen an elimination and forming the double bond. This is not in our interest as in this case. Okay? Thank you so much for watching and see you in the next video. Peace!